Okay, rational functions. A rational function is one where you have the numerator is a polynomial and the denominator is a polynomial. So basically it's the quotient of two polynomials. Here's some examples of them. To find the domain of rational functions, you have to find where the function is undefined and then the domain does not exist there. So for instance, with rational functions, wherever the denominator is equal to 0, the function is not going to exist. So it says the domain of a rational function is the set of all real numbers that are not zeros of the denominator. So to find the domain, we need to set the denominator equal to 0 and solve. So for letter A, the only number that would make that undefined would be 0. For letter B, you would have to factor the denominator.
So all real numbers except 0 and 1.
So you would just say x cannot equal 0. For letter B, we would factor it, and we'd get x minus 4 and x plus 2 when we factor it. So positive 4 and negative 2 would be where it would be undefined. So that means the domain would be all real numbers except for them, which I got rid of them. So I would say that the domain here, x cannot equal 0, and here x cannot equal 4 or negative 2. Because those are where the denominator is equal to 0. The intercepts of a rational function. Okay. The x-intercepts are the zeros of the numerator. And the y-intercept is when how do we find the y-intercept? When x is equal to 0, right? Okay. So the x-intercepts of a graph of a rational function occur at the numbers that are zeros of the numerator, but they're not zeros of the denominator. Okay. So the x-intercepts are zeros of the numerator, but not zeros of the denominator. And we'll talk about that in just a moment, because if you remember, when that happens, you have the same 0 in the numerator and denominator, you have what? A whole. That's right, a whole. Okay. So the first thing we're going to do is we're always going to factor if we can. Must have deleted it all. So we have x minus 3 and x plus 2 would be in the numerator. All right, so the x-intercepts are where the numerator equals 0. And where does the numerator equal 0 here? Okay, so 3 and negative 2 are the x-intercepts. The y-intercept, there's only one, right? The y-intercept in this case is 3. Put 0 in for x. Okay, that means that the first two parts in the numerator go away, right? They're 0. The x in the denominator is 0. So what's negative 6 divided by negative 2? 3. So to find the y-intercept, all you have to do is take the constants and divide them. Okay? Y-intercept is the quotient of the constants. Okay? Right. All right. Now, we have some vocabulary we just need to talk about. Continuity. Unlike polynomials, Rational functions are not continuous because there are places where the denominator is equal to 0, and so the graph cannot continue to move from left to right because at some point in time there's going to be a break in the graph. Otherwise, the graph is a smooth curve. So otherwise, it is like a polynomial except for where the denominator is 0. Vertical asymptotes. They occur at every place the denominator is equal to 0, but the numerator is not. Okay? Vertical asymptotes where the denominator equals 0, but the numerator is not. And this might all basically be on that sheet I gave you. Holes, places that a 0 occurs in both the numerator and denominator, we have a hole, except if the degree of the 0 in the denominator is greater. Okay? So if the degree of the 0 in the denominator is greater, then we have a vertical asymptote. So for instance, if I had this, okay? So both the numerator and denominator have x minus 2 in it, but since the degree of the denominator is 3 for that common factor, it's bigger, then I would still have a vertical asymptote here. I would not have a hole. Okay? End behavior. And the end behavior is a couple different things. It could be a horizontal asymptote, or it could be what's called an oblique or parabolic asymptote. Depends on the situation you're in. So when x is large, so we're talking about very, very large values of x, very, very small values of x. A polynomial function behaves like its highest degree term. Remember we talked about that with end behavior, right? Okay, if it's a third degree, I know that it's going to go, one end's going to go up, and the other end's going to go down. If it's a even degree, they're both either going to go up or go down. As shown in section 4.3, okay, for a rational function, the end behavior is determined by the ratio of the highest degree term of the numerator over the highest degree term of the denominator. All right, and we're going to take a look at that and be very specific with how we look at them. So then we're going to end up identifying zeros, asymptotes, and holes of each function and graph them. And for the most part, you should be able to graph these actually without a calculator. All right, you're smart enough, you should be able to do that. Oh, hey, look at that. Goodbye.
So could we use a calculator? Or are you saying basically we have to use our brain?
I'm saying you need to be able to use your brain. All right, so here we go. These are on your paper, right? No? Okay. Okay, they're not. All right. Okay, so let's take a look at these. All right, letter A. Where is it equal to 0? That's where the numerator is equal to 0. Where at?
Should we write these down?
You can. Yep. You're going to end up needing graph paper for this stuff too. So, where's the numerator equal to 0 at? Okay, negative 2/5. Okay. Vertical asymptotes. One thing to remember with vertical asymptotes, it is a line. Okay? Horizontal asymptotes or other kinds of asymptotes are lines. All right? So where's the vertical asymptote here? And that's when the denominator equals 0. Okay? So x equals negative 1. Now, when we're talking about horizontal asymptotes or we're talking about end behavior, okay? This all goes in the same discussion. Take the largest degree terms of the numerator and the denominator, okay? What's the largest degree term in the numerator? 5x, right? Okay. The largest degree term in the denominator is? Is x, okay? So if I take those two things and I simplify it, what do I get? So the horizontal asymptote is y equals 5. So horizontal line. Now, are there any holes here? Do they have, excuse me, a common factor in the numerator and denominator? No, so there's no holes. Okay? Letter B. So if it needs to be factored, that's the first thing you're going to do. So here we have x minus 2 over x squared plus 6x. So we're going to factor the denominator. We get x times x plus 6. All right. So where does for the zeros, where does the numerator equal 0 at? Okay, so I have a 0 at 2. Vertical asymptotes. Where does the denominator equal 0? And okay, it's 0 and negative 6.
You just know it's 0 because there's no other number.
Because it's x. What makes x equal to 0? When it's 0. Okay, vertical asymptotes. All right. Now, in this case, what's the highest degree term in the numerator? X. What's the highest degree term in the denominator? X squared. So when I simplify that, what do I get? Excuse me. 1 over x. Now, 1 over x is not an asymptote. But think about it for a second now. When we're talking about horizontal asymptotes or end behavior, we're talking about very, very large values of x. So if I take my calculator and I put in my y equals 1 divided by x, and I want very, very large values. So I'm going to go to my table setup, and I'm going to go by, come on, 100s. So what happens as the value of x gets bigger and bigger and bigger? What's happening to the value for y? It's getting what? Smaller. Is it going into the negative numbers? No. So in other words, it's when it gets smaller, it's getting closer and closer to what number?
0.
0. So in this case, you have the answer is going to be y equals 0, because when you have very, very large values of x, the number is getting closer and closer to 0, so the asymptote is y equals 0. Do we have a common factor in the numerator and denominator? Is there a common factor in the numerator and denominator? The answer is no. I have x minus 2, x and x plus 6, so there are no holes then. So letter C, I'm going to factor this whole thing. So in the numerator, what do I get? Okay. X minus 3 and x minus 2. All right. In the denominator, we have what? Okay. Now, so what do we have? We have a common factor, right? So if I took just that information and I wrote down my zeros, what would my zeros be?
3 and 2.
Okay, 2 and 3. All right. So all Right? So we would have 2 and 3. All right? What would be my vertical asymptotes then? Okay, x equals 1 and x equals 3. Well, there's a problem here. I can't have a 0 where I have a vertical asymptote because you're telling me...
Interruption. Any freshman who needs to have...
So we can't have the graph cross the x-axis and the graph be undefined at the same spot. So that means that I can't have either of those things. So that's where we have a hole. So there's a hole at 3. Now, the vertical or horizontal asymptotes then. Okay? We take, to find the end behavior, we take the largest degree term of each of the numerator and denominator. What is it in the numerator? We got x squared and x squared, right? What's x squared over x squared? 1. So y equals 1 would be my horizontal asymptote. So here's the way with these two things, okay? Now, in letter A and B, okay, when we were dealing with the horizontal asymptotes, the degree of the numerator and the degree of the denominator were the same, okay? The degree of the numerator was 1, the degree of the denominator was 1. So I took 5x over x and got 5. Okay? In letter C, the degree of the numerator and denominator were the same. Again, x squared over x squared is equal to 1. Okay? So if the degree of the numerator and the degree of the denominator are the same, then your horizontal asymptote or your end behavior is just going to be the ratio of your leading coefficients. Right? Leading coefficient here is 5, leading coefficient there is 1. Leading coefficient here is 1, leading coefficient there is 1. Okay, 5 over 1 is 1, 1 over 1 is 1. Okay? In letter B, here we have a situation where the degree of the denominator is larger than the degree of the numerator. Okay? Whenever that happens, you get y equals 0, because you'll always end up with a constant in the numerator and x squared, x cubed, whatever in the denominator. All right, so we'll look at, so there's 2 of the 3 instances that could happen. We'll take a look at the other ones later on. All right, so let's look at graphing these. All right, let's start with letter A. All right, so first of all, I've got a 0 at negative 2/5, so I'm going to mark that spot on my graph. Negative 2/5 about here. It's equal to 0. Says I have a vertical asymptote at negative 1, horizontal asymptote at positive 5. So that means I'm going to draw dotted lines to represent those asymptotes. So a vertical one at negative 1, horizontal at 5. So negative 1, I have a dotted line, positive 5, I have a dotted line. All right. Now, we know there's no holes. Okay. Let's see, for graphing purposes also, it'd be nice to know what the y-intercept is, right? Okay. So what's the y-intercept? For letter A, what's the y-intercept? It's the ratio of the constants. 2 divided by 1 is 2. Okay. So y-intercept is 2. Oops. Hey, look at that. That's cool.
why the numbers
Okay.
aren't with X over here.
Yes. Okay. So, what does it mean for something to be an asymptote again? The graph gets closer and closer to it, but never touches it. Now, okay, with more advanced problems, sometimes the graph will cross a horizontal asymptote, but it'll still use the horizontal asymptote. We'll show you how that happens in a minute. But usually it doesn't. Okay, sometimes it does. And how we can figure this out is usually pretty easy. But right now, though, I can see where those 2 points are, so I know what my graph's got to look like basically. That this graph has got to come from down here, go up here, and then it's got to come along the x-axis. Or along the asymptote. It doesn't come back down. Make sure you don't have it coming back down.
Putting it down at -1.
What's that?
What was the point of doing the
Right there?
vertical asymptotes?
Because they can't go across it. Okay. All right. Now, your graphs, all right, are going to be then, if I have graph down here in the fourth quadrant, okay, basically, right? Okay, if I cut this, use my asymptotes to cut it into quarters, okay, fourth quadrant, then where's the rest of the graph got to be? Okay, yep, it's got to be up here then. Now, how can I verify that? If I didn't have a calculator in my hand, how could I verify that? Okay, exactly. All right, so I'll pick a number on the left of the vertical asymptote, x equals -1. All right, so pick a number over there. Let's use 5. That's a nice number. Okay, -5. So if I put in -5, I'd have -25 plus 2 over -5 plus 1. Right? Okay. And -25 plus 2 is -23, right? Okay. And -5 plus 1 is -4. Okay. What's -23 divided by -4?
Not a good number.
It's a positive number, first of all, right? Okay. 23 divided by 4 is almost 6, right? 23 divided by 4, since 24 divided by 4 is 6. 23 divided by 4 is almost 6. So at -5, my number that I get is going to be almost +6. So it was above the asymptote. Okay? And you could check to see if your graph ever goes above the asymptote by picking a positive number in the same area. Okay? Quite a ways away. Most of the time it's not going to happen. So, all right. So there's our graph of letter A. Let's also graph letter C. Letter C, we have a 0 at 2. And then we have horizontal and vertical asymptotes at +1. Okay. So my horizontal and vertical asymptotes are at +1. I have a 0 at, what did I say again? 2. Okay. Now we also have a hole, right? A hole at 3, at x equals 3. So here's how you graph your hole. Okay, because you need to figure out exactly where it is. Okay. And it's very simple. Okay. If I look at this function, those cancel, right? The x minus 3's will cancel. All right. Now put 3 in for x. That's where your hole goes. All right. So to find out where the hole is graphed exactly, you cancel anything from when you factored it, and then you put that x value in to what you have left. So we get 3 minus 2 over 3 minus 1. So that's 1 over 2, right? So my hole is going to be at the point 3 and 1/2. So I'm going to put a hole there. Now what really helps me with graphing this is the y-intercept. Where's the y-intercept at? Go back to the original function.
Oh, wait, 2 divided by 6 by 3.
Okay, 6 divided by 3 is 2, so my y-intercept is at 2. All right. This helps me because it tells me then for sure that I'm going to have a graph down over here, okay, in basically the 4th quadrant, and my graph's going to be up here in the 2nd quadrant. So my graph's going to look like this. Now, how could I make it more accurate? Plot more points, right? Find more points and plot them. So those are the main things, okay? Tomorrow, and we're going to talk about what's called an oblique and slant asymptote, or those are the same thing, oblique asymptote, slant asymptote, same things, and parabolic asymptotes. And those are going to be when the degree of the numerator is larger, okay? So we looked at finding the zeros when the numerator equals 0. Vertical asymptotes when the denominator is equal to 0. And those are the same spots where it is undefined. Okay? Holes if I have a common factor in the numerator and the denominator. Okay? And you have a horizontal asymptote for your end behavior when the degree of the numerator is the same as the denominator. It's the ratio of the leading coefficients. If the degree of the denominator is larger, like it was in B here, it's 0. Exactly 0. Okay. All right. And then you can draw the graph. So I want us to take letter C here, and I want you to graph it on your calculator. It better look exactly the same. Make sure you use your fraction key. All right. That reminds me, I forgot to fix somebody's first hour. Okay. Make sure you use your fraction key. That way you're going to be much more accurate. Or
Interruption. Any sophomore who needs to have picture retakes done or did not have first time, please go now. Thank you.
Oh.
okay, now make sure everybody does this. I want to make sure your calculator produces the same thing as mine does. All right? Because I have a couple of students that are going to be in next hour, I know, that have 83s, and we're doing similar stuff with Algebra C. So, all right, now, is there a hole there? Can you see a hole?
No.
But if I hit trace and type 3 and enter, I get no response. Okay. So if I zoom in around x equals 3, or if I look, let's look at my table first of all. On the table, oops, at x equals 3, I have an error. Okay. So I know it doesn't exist there, yep, because there's a vertical asymptote at 1. So that's why there's an error there at 1, because there's a vertical asymptote. At 3, there's an error which, vertical asymptote. But it should also be 0 there, right? The calculator's not going to give you both. So if I change my window so I'm focused right around positive 3, so if I go from 2 to 4 with my x, and graph it, let's see if that'll do it. All right, I can see it on mine. Let me just make my window different too. The y's. Oops. All right, my y is just going from 0 to 1, so I'm not going to see the whole thing. But I can see that at x equals 3, there's a hole there, okay? No pixel. All right, that proves to me that there is that hole that I had to put on my graph. So when I actually do graph that, I've got to draw a hole in there, okay? All right.
So, are the holes basically like the